All right, so the next example that we're going to do is going to build on what we've done already with the calculator circuit. So what you're going to do for this exercise is put the calculator that you already have in the context of a pipeline called calc and put all that logic in stage 1. Just to be explicit that the logic is in a named pipeline, in a particular pipeline stage. And then I also want you to take the counter that you developed and also put that into stage 1 of the same pipeline. And then you can check the behavior in your simulation. All right, and then we're going to build on this in subsequent exercises. But again, you can stop the video, and when you have that, start it up again. All right, so now you've got your calculator and your incrementer in a pipeline, and now we're going to make some changes to that design. So if we're going to run this calculator in a high-frequency circuit, we might need 2 cycles to perform the operation, just like we needed to break up the Pythagorean theorem computation. Now we're going to divide up your calculator. So in the first stage, we're going to perform the operation. In the second stage, we're going to select the results based on the select. So we're going to make modifications to the circuit as depicted here. So you're going to move the multiplexer to a second pipeline stage. And we're going to perform calculations now every other cycle. So perform a calculation in one cycle, and then the next cycle, the inputs are meaningless. And then, now that our calculator is iterative, right? Every computation is based on the result from the previous. So we're looping that output back to the input. And now that it takes 2 cycles to perform the computation, we're going to loop that value back with a 2-cycle latency, not with a 1-cycle latency. So you're going to modify your circuit to implement this picture. So just calling out some of the elements here for you to do that. I guess I'll step through these one by one. So in the first step, you'll change the alignment of out. So you'll have the output loop back to the input with a 2-cycle latency. At this point, the multiplexer is still in the same stage as the addition, subtraction, multiplication, division. So you basically get 2 staging flops and then the recirculation. Then you're going to change the counter to be a single bit counter. So what's this counter doing for us now? Now that we're performing computations every other cycle, we need to keep track of whether it's a compute cycle or a meaningless cycle. And we'll do that basically with a toggling bit. And that's the same circuit that we've done for our incrementer, but it's a 1-bit circuit. And if you have an incrementer that's operating on 1 bit, it goes from 0 to 1, back to 0 to 1 to 0 to 1. So we've just created essentially an oscillator, and that's keeping track of even and odd cycles for us. So we're going to have that circuit deciding whether the computation is valid. So that's generating this valid signal. The third step you're going to do is you're going to connect the valid as the connect the valid together with reset to decide whether to drive the output with a 0 value. And this is just going to drive 0 in the cycles that are invalid. Right? So if we have a reset or we have or we're not valid, then drive the output with 0. Fourth step, you'll retime the mux from stage 1 to stage 2 and end up with this picture. And then you can verify the behavior in the waveform. And what you should see in the waveform is that we're performing a calculation every other cycle. All right, so again, you can pause the video and try that exercise.